Let's say we're asked to make a function for the following sum. So we're given the sum from I equals 0 to n of I squared. What does this mean? Well, it means that you start with an I value of 0, so 0 squared, plus 1 squared, plus 2 squared, plus 3 squared, and that continues forever until you get to n squared. Okay, that's what that means. Now, how can you make a function for this? So one thing we can do is we can make a table, right? I can say that we have some n values, right? Your n values are 0, 1, 2, 3, right? And that continues, right? You get to 4, keeps going. And we can write what the sum to that point is, right? So the sum from I being 0 to n of I squared. What's the sum of the 0th term right there? What's your sum up to that point? Well, it's just 0, right? When you get to the second point, your sum is just 1. When you get to the third point, your sum is, well, 2 squared is 4, plus 1 plus 0 is 5. When you get to the next point, your sum so far is 5 plus 3 squared, which is 9, which is going to give you 14. So your sum up to there is 14, your sum at the fourth term is going to be 30. You can just keep continuing like that. And now this really does serve as sort of a table of values, except it's kind of tipped on its side, right? And we can ask ourselves, what's the first difference here, right? From this term to this term, you're adding 1. From this term to this term, you're adding 4. From here to here, you're adding 9. From here to here, you're adding 16. And so because these first differences are all different, this is not a linear function, right? Now, if you check the second difference, from here to here, here to here, here to here, you get plus 3, plus 5, plus 7. So it's not a second difference either, meaning this is not a quadratic equation either, right? It's not a quadratic function. Now you check the third difference, and you see you get plus 2, plus 2. These are the same. So that tells us that this must be a third degree function, or a cubic polynomial, or a cubic function, whatever you want to call it. And so if we wanted to design the function that describes this scenario, you would say that the sum is equal to some value n cubed plus some value n squared plus some value n, plus some constant, right? This is generally how you would write in standard form a polynomial of the third degree, right? This is a cubic function. Now, what you can do is you can solve for a, b, c, and d, and then you'll have an actual function at the end of the day that represents this sum for any given number of terms, right? For any value of n. All you'll have to do is plug in n, and it'll tell you the sum for that many terms. So what do we do here? Well, we know that when n is equal to 0, the sum is 0, right? Because you remember that from our table up here. We said that if you just have the first term and n is 0, your sum is going to be 0, right? So because the sum is 0 and n is 0, we can plug in 0 for all your n's and then set the sum to 0 as well. So 0 is going to equal 0 plus 0 plus 0 plus d. Therefore, d is equal to 0, right? D is left on the right side, 0 on the left, so d must equal 0. So we just found one of our numbers, right, of the 4. Now, how can we find the rest of the numbers? Well, we know that when n is equal to 1, the sum was equal to 1, right, from that table. And so when we plug in 1 for all the n values, you set the sum to 1. So 1, the sum, is equal to a times 1 cubed plus b times 1 squared plus c times 1. Meaning that 1 is equal to a plus b plus c. So that's a definition we have. Now we can save that, and we'll come back to it. Now, what about when n is equal to 2? When n is equal to 2, we said the sum was equal to 5, right? You can reference that table before. We said the sum was equal to 5 when n is equal to 2. So we can say 5 is equal to a 2 cubed plus b 2 squared plus c times 2. Simplify all this, you get 5 is equal to 8a plus 4b plus 2c. So that's another equation we have. So we have this equation, and you have this equation so far. So we're going to save both of those, and we're going to keep going. We need another equation, because if you have 3 equations and 3 unknowns, you can solve for all your unknowns, right? All your variables. You need the same number of equations as unknowns in order to solve for them all. So we have 3 unknowns, a, b, c. We have 2 equations so far, so let's make a third equation. Let's look at the next sum. We know that when n is equal to 3, that the sum we said was equal to 14, right? And so we can say 14 is equal to a times 3 cubed plus b 3 squared plus c times 3. Simplify that, you get 14 equals 27a plus 9b plus 3c. This is your third equation. Using these 3 equations, we can solve for a, b, and c, right? We're going to write a plus b plus c is equal to 1, 8a plus 4b plus 2c is equal to 5, and 27a plus 9b plus 3c is equal to 14. So all you have to do here is solve the system of equations. You can do that using technology, you can do that using substitution, or you can do this using elimination, right, if you want to do it by hand. So currently, I think most of you would try to solve this either with elimination or substitution, right? And it's completely up to you. So you would solve 2 of them first, you'd get a definition for a couple of these, and then you would plug that into the third one, and then you could solve one of them. It's a long process, right? So you solve that system, and I'm going to leave that to you to work on, right? Try that on your own and see if you get these answers. The answers should be for a, b, and c. A is equal to a third, b is equal to a half, and c is equal to 1/6. And if that's the case, you can say that your function is 1/3 n cubed plus 1/2 n squared plus 1/6 n, and that is equal to the sum from I equals 0 to n of I squared. Meaning that if you have a series of 0 squared plus 1 squared plus 2 squared plus 3 squared, any number of terms, right? You can go all the way up to 100, make n whatever you want. You just plug the number of terms into this equation, and it'll give you the sum of all of those terms. So this is the function for the sum. And if you want, you can even factor this, right? So we could factor out n as a common factor, and you could also take out 1/6. So you take out n over 6, and you would be left with 2n squared plus 3n plus 1. If you want to factor it, factor the inside using decomposition, and you would say 2 times 1 is 2. So you want 2 numbers that multiply to 2 and add to 3, so 2 and 1. So you'd have 2n squared plus 2n plus 1n plus 1. Factor by grouping, 2n, n plus 1, plus 1, n plus 1. Therefore you'd get 2n plus 1 times n plus 1. Just a review of decomposition, hopefully you remember that. So you write that out here, 2n plus 1 times n plus 1. And you could clean up your answer a little bit, make it look a little nicer. You could say n times 2n plus 1 times n plus 1 all over 6. So that's the factored form. So you can leave it like this in standard form or factored form. Regardless, those are each your cubic functions that represent the sum.